I wanted to follow up on some of the lecture from today, and so the part that I want to talk about was Ampere's law. And again, Ampere's law we have on the left-hand side, we have this line integral, and it equals our constant U naught times the current through the surface that your line integral makes up. And so here's a little picture on the right there. And we want to talk to this, we did this in relation to solenoids. And so a solenoid is basically a bunch of wire loops together. So here's one wire loop. We call this the magnetic dipole. And you see that it causes a magnetic field this way, so there's a north side here and a south side here. And what happens is if we get a number of these wire loops together, you get a very constant or uniform magnetic field inside here. Remember the sort of how pushed together the lines are, how dense they are. It tells you how big the field is. So it's a very large magnetic field, and the field is much weaker outside here. Okay, so much weaker that we essentially call it zero compared to the field inside the solenoid. And you'll see that this is basically it just sort of mocks the exact same one loop. We had north on the one side, south on the other side. Here a large number of them does the exact same thing. And this basically looks just like having a bar magnet. And applying Ampere's law, so we have the B dot ds business here equals U naught times I. And so here's our loop. We make our loop like this here. So there's 4 legs of the loop, 1, 2, 3, 4. And so there's 4 contributions. And so let's say we start at this point right here. So when I go, and we're going to go in a counterclockwise fashion. So when I go through this part right here, again, that the line integral is telling us how much our B field is perpendicular, is parallel to our loop. So at point 1, it's exactly parallel. And so we have B times L for that first leg. All right, now when I go through the second leg, so again we're saying the B field here points this way inside the solenoid, and it's 0 outside the solenoid. And so when I do this part of the loop here, half of it, the B field is 90 degrees. When the B field is 90 degrees, the line integral is just 0. The other half is purely 0. And so I add a 0 for that leg. Over here, leg 3, over here, we're assuming that the B field is 0, so that cancels out. And then finally, leg 4, the B field is 0 here, and again, it's at 90 degrees here, and so it would be 0 for the segment number 4. So basically, there's 3 zeros here that we're adding up, and then that equals U naught. And now, so this is the current through. Is how we call it. And so the current through, basically there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 currents. I'm just going to say capital N for the 12 times the current that's in each one of those loops. All right, so I get B times L equals U naught N over I. And when I solve for the B field, I get N divided by L times I. And then what we do is you typically write N over L as just lowercase n. And again, so here, for me, for instance, this particular case, this turns out to be 12 divided by L, but in general, you can just do this for the complete length. Okay, so here, if you look on my picture, there's actually 12, 13, 14, 15 loops. Okay, so it's the same ratio. 15 divided by the total length is the same thing as the length of my square, 12 divided by the length of my square.